With the recent advances in 3D acquisition technology, 3D content such as humanoid character models are now readily available. However, when imported in virtual or augmented reality applications, these contents are only static. They do not move. Although there are already existing algorithms which allow for these characters to move, most algorithms require certain prerequisites. First, the pose of the character model should be within the bounds of what the system can handle. Second, to allow for a more appealing virtual realism, character models should not have conjoined body parts, as these parts might have artifacts when animated. However, these prerequisites present problems when applied to real-world character models. The rationale is configuring pose restrictions and separating conjoined body parts may not even be possible for rigid toys, sculptures, or figurines. In this video, we present an interactive system for automatic skeletal rigging of 3D humanoid character models. Unlike other skeletal rigging techniques, it does not require any prerequisites such as specific pose or no conjoined body parts. If the input have conjoined body parts, the system provides an interactive cutout tool to separate them. Afterwards, it implements hierarchical mesh segmentation to infer the skeletal structure. It then performs a smooth skinning technique. Within minutes, the input can then be used to set up skeletal-based animation in most animation software applications. The click-based cutting system allows user to fully cut or slice the mesh. The user is initially presented with a triangle character mesh that contains conjoined body parts. On top of the mesh are candidate points providing suggestions based on the mesh concavity. Afterwards, the system asks the user the type of cut and the boundaries where the cut is intended. The cutting contour is inferred from a feature-sensitive metric given several points of intersection. Mesh cutting uses the contour calculated from the user's input to properly identify the edges where character mesh is to be separated. Note that the system reaches a global minimum as the generated cutting contour passes on the same path despite the differences in user inputs. Afterwards, it automatically fixes the separated mesh by surface regeneration and refinement. Finally, the cut mesh is then passed on to the automatic skeleton generation system. The mesh is converted to the global point signature surface representation and hierarchical mesh segmentation is implemented to identify the joint positions in the body. The character skeleton is then built given the different joint position. Skin attachment on the skeletal structure is performed by assigning bone weights based on the proximity and is distributed over the surface using heat equilibrium. We show the differences between the animation of uncut mesh model and the mesh model cut by our system. Although the skeletal structure of the uncut mesh models are correct, artifacts arise when they are animated. On the other hand, those models from our system show a more appealing virtual realism.